Hello and welcome to another episode of the Oxford MAT Livestream. I'm James and I'm joined again by Flora.
Hi, I'm Flora.
We're going to start with some maths like always. Here's some maths that is in the revision warm-up bit of maths from the worksheet, but I'm going to do it on the board just because I really like it. It works like this. It's the easiest number to prove to be irrational. Let's write that out. Easiest proof of irrationality. So an irrational number is one that you can't write as p over q for whole numbers p and q. It's sort of weird that these exist. Weird if you only believe in fractions, I suppose. And there's this proof that lots of people know, maybe you learn it in school or something, that the square root of 2 is irrational. There's this proof to work out the square root of 2 is irrational. At university, someone showed me proof that's simpler, it's easier. So it's easier to prove that this number is irrational. The proof works like this. Suppose that this number, natural logarithm of 2 divided by natural logarithm of 3 is rational. Suppose that it's p over q for some whole number p and q. Okay, this is going to go immediately to some sort of contradiction. Something's going to go wrong really quickly with this. Okay, we can multiply it up, so we can write q log 2 is equal to p natural log 3, and then do e to the power of each side, exponentiate each side to get, well, what do we get? We get 2 to the q is equal to 3 to the p. But this number on the left is even, and this number on the right is odd. That's a contradiction. So it can't be irrational. So it can't be a rational number. You can't have an even number equal to an odd number. So the thing we suppose at the top must be wrong. That this thing can't be a fraction. Brilliant stuff. Right, hello to people in chat. Hello to Sophia and Rebecca. I can see an anonymous person, and Tommy, Lily, Jake, Molly, the complex number user, SB, Becca, Patrick, Jake, Bruh, Anonymous, again, Zach and George and Payne are here. Hi to people joining in the Slido chat. If you want to join us in Slido live chat, currently being moderated by Flora. Thank you, Flora. It's under there, and it's on slido.com/matlive. Brilliant stuff. Okay, that's
Great.
my proof. It's a small thing I skipped over halfway through near the end of that, but we're not going to talk about. Technically, I should tidy it up a little bit by worrying about whether P and Q are worrying about whether these are 1 or not, whether these are 0. They're not 0, but maybe I should just put that here. There we go. Cool. I mean, they're obviously not 0. This isn't 0. You can't divide by 0. I don't like saying that stuff when I'm going through the first time. Had you seen this before, Flora?
I'm not sure that I've seen this exact proof before. It's hard to remember. I've seen that many proofs at this point.
Okay. I really liked learning this at university as a slightly faster proof of irrationality. Okay. And it's got that structure of proof by contradiction, where you suppose something's true.
Yeah.
It turns out, oh no, at least disaster. Okay.
Someone's asking for a how was your day, Paul?
Yeah, all right, let's go. How was your day, chat? How is it going? So Slido has live polls in, which we do at sometimes during the day. Normally people vote for that they like maths more than they like their current day. So let's have a quick look
I
at
don't know, the day's going pretty well today.
Oh no, that's all right, isn't it? Hang on,
Yeah.
I'm just gonna make that bar chart taller. Sorry, Flora.
Oh, it's fine, don't worry.
I've replaced you with a bar chart. On screen at the moment is the maths that we're going to be talking about today. Oh, I might have done something weird to the volume there. Who knows? There's no math syllabus material on what we're going to be talking about today. I considered having a kind of other maths section at the end, but then I thought, no, let's try and sort this into primes and proof today and recursion next week. Okay, so here's some content on primes and proofs that you're expected to know, even though it's not explicitly on the maths syllabus. Facts about what it means to be prime, what divisors are. You don't have to have seen this proof about things being irrational. This is my example of showing that something's true by assuming the opposite and showing that leads to nonsense, proof by contradiction. And there's words like necessary, sufficient, and counterexample that we're going to explore a bit today as well.
Yes.
Looks like people's days are going all right. Should we have to vote for primes and proof as well?
Yeah, that's a good idea.
Let's turn that one on. Okay, so separately, 3.6, not so great today. Hopefully we can improve your day a little bit by talking about prime numbers for an hour or so. We'll see if that works. People are currently voting for how they feel about primes and proof at the start of the session.
No, that looks pretty good.
Oh, it's going well so far. And the fastest people to vote are usually very excited about topics. Is he 4 stars taking over from 5 stars now? People less keen, now 3 stars. People less keen on primes and proofs, getting into Slido, letting us know that they don't feel quite so happy about primes and proof. It's quite a big topic. It's got a lot of things going on, hasn't it? Lots of things that you might need to do to prove something. Lots of tricky logical traps and things to jump over, which we're going to try and look at today. Okay, people have voted for about 3.5 on how they feel about primes and proof. I think it was about 3.6 on how your day's going. So.
Close.
My theory.
Someone's asked us how our day is going.
Oh, that's nice.
I appreciate that. My day is going quite well, thank you.
Yeah, I'm all right too. I'm switching on. There we go. Okay. Thanks for asking.
Cool.
Weather's gone terrible. We're now in jumper weather, but maybe that's not a bad thing.
It is raining. That is a true statement.
Cool. Okay.
Shall I jump in with some warm-up questions?
Yeah. Someone's asked a question in chat. Does my proof also work for any other logarithms that are relatively prime? Great question. Can you do it for other numbers that are relatively prime? Great question. Try it yourself by writing down some powers. Yeah, I'm not going to answer that. I'm going to let you answer that. Cool. Okay, over to Flora for some warm-up maths.
Okay, so I'm going to start off with 3 questions which I've circled here, which are kind of related to each other, and if you can spot the link, well done you. You will spot the link once I've done them. Okay, so firstly it says work out 45 squared. If you can do this in your head, creds to you. You're supposed to do it without a calculator, so if you want a little method to kind of check that you're doing it right, the way I was taught when I was a child was draw a grid like this, and then you kind of multiply each part separately, and then you know that you've not missed anything. Some people can do like a column multiplication thing, which is basically the same thing, but you write out less. So then I've got 1/600 plus 400 plus 25, add them all together, and you get 2025. And so you're thinking, okay, how am I going to use this to factorize 2021? Well, you've got to use the fact that 2025 is very close to 2021. And when you think about factorizing things, what does factorize mean? It means, well, write it as a multiplication of some different things. If you want to write 2021 equals something times something, you can use a nice little trick, which we call the difference of 2 squares. Hopefully you will have heard of this before. It's the fact that a squared minus b squared is equal to a plus b, a minus b. If you don't believe me, you can write out by expanding these brackets. You have a squared minus ab plus ab, and then minus b squared. But of course, minus ab cancels with plus ab, so then you see that it is equal to a squared minus b squared. Now this little fact may seem like, well, okay, that's just a nice little algebra thing, but it actually is really useful for actual numbers and algebra and proofs and all sorts of things, which is what we're going to demonstrate here. So back to the 2025 problem. We're trying to factorize 2021. Now, I don't know about you, but it seems quite clear to me that 2025 minus 4 equals 2021, right? And 2025, as we know, is a square number because we just worked out that 45 squared is 2025. And hopefully we all know that 2 squared is 4. So we could rewrite this as 45 squared minus 2 squared equals 2021. And now well done to anyone who spotted what I'm going to do next, because if you think about what I wrote above, here we have A is 45, B is 2, so we can actually write it as 45 plus 2 times 5 minus 2. It doesn't matter whatever numbers you put in, it will still work. Equals 2021. And so then we can obviously just write 2021 equals 47 times 43, and we have factored 2021. Nice little aside is that 43 and 47 are prime numbers, so we have actually done a prime factorisation of 2021. And you may want to remember that. You know how questions always come up that are to do with the year. Like when you're going into an exam, like a UKMT challenge or whatever, like you may want to look up the prime factorisation of the year that it is. Just in case it comes up.
We've talked about this before. It's not MAT questions don't use the current year as much as some UKMT question stuff is.
No, UKMT does, and so, sometimes some courses, like a number theory course, might.
Factorising 2021 is not that hard, especially if you spot this difference of two squares trick.
Exactly, and now you know.
Yeah, you know this is actually a good trick for factorising. 2021 is a big number that's a product of two quite large primes. Spotting that it's 4 less than a square gives you a way to crack that open and factorise it like that, which is in some sense actually a good algorithm, but it's a good algorithm sometimes for factorising numbers.
If a number is a difference of 2 squares, then it's very useful.
Difference of 2 squares, Becca says, constantly popping up in maths, which
it's very true.
We will see difference of squares again.
It pops up when you least expect it, and I don't know whether you're expecting it in the next question, but here we go. Are there any primes of the form n squared minus 1 where n is a whole number? I mean, spoiler alert, difference of 2 squares. N squared minus 1 can be rewritten as n plus 1, n minus 1. Here we have like n is functioning as a from above, 1 is functioning as b. So you have n plus 1, n minus 1. And that's n squared minus 1. So are there any primes of this form? So what do we know about a prime number? Well, a prime number, hopefully you all know, is a number which only has exactly 2 factors. So it's a number, it can't be 1. It's a positive number, which is a whole number, and it has factors of only 1 and itself, no other factors. So if a prime number is equal to n squared minus 1 for some n, then it's equal to n plus 1 times n minus 1 for the same n. So we have written our prime number as the product of 2 different numbers here. And you know that these 2 different numbers are positive integers because n is a whole number. So these are whole numbers too, n plus 1 and n minus 1. So you've written your prime number as a product of 2 positive numbers. So basically, one of them has to be 1 and one of them has to be the prime number. Otherwise, it's not a prime because it would be a product of 2 other numbers, which means it has other factors other than just 1 in itself. So here we have to have n minus 1, which is obviously the smaller number, is equal to 1. So n is equal to 2, and n squared minus 1 is 4 minus 1, which is equal to 3. So are there any primes of this form? Well, yes. There's 1, which is 3. And 3 is the only one. And we've shown through this argument that 3 is the only possible one that could exist, because if you had some other prime, like if n was a different number, then you wouldn't have 3, except you would have a number that was a product of 2 different numbers, which were not 1 and not the prime number. So it wouldn't be a prime, and that would be a contradiction.
Question in chat about whether you can just write down n equals 2 and say, well, that's 3, so the answer is yes. I think that works.
Yeah, I think if it was like an exam question, it would probably say like, is the 1, is the a unique one, are there infinitely many, are there none, and then you would have to like circle the right answer or something like that. In this context, they have phrased it as a yes/no question, so you can just say yes, there is 1.
Literally, a very logical interpretation of the question is, yep, it could be a...
Yeah,
so
it is a yes or no question.
Yeah.
So fair enough, the answer is yes.
Cool, okay.
Cool.
I like the way that there's only one solution.
Yeah, it's kind of satisfying.
We don't know a huge amount about prime numbers, but writing down a particular form, a particular expression, here n squared minus 1, and asking are there any primes of that form, that is something that we can talk about. Like we've just done a question like that. I think we're about to do another question like that.
Yes.
Somehow
so,
answering questions like that works.
Yes, so I'm going to go kind of to the right more, maybe. I'm going to look at this next question. Are there any primes of the form n to the 4 minus 16 where n is a whole number? So you're thinking, okay, it's kind of similar to the previous one, except here we have n to the 4, so it might be slightly more complicated. But what you've got to remember about even powers are, you can kind of make it be n squared to the something, or n to the something squared. And if that made no sense to you, allow me to write it down instead. So you've got n to the 4 minus 16. So n to the 4 you can also think of as n squared squared. And if you think of it that way, then you've got n squared squared minus 4 squared, which is of course 16. So you guessed it, it's difference of two squares. So here we have n squared plus 4, n squared minus 4. And now there are two different ways to do this. And the first one is like what we just did. The other one is kind of cool. Anyway, so the first thing to think of is similar to what we just did. You have a number which is supposed to be prime, and we factored it into something times something. So basically, one of them has to be the prime number and one of them has to be 1. Otherwise, it's not a prime number. So something squared plus 4 is going to be bigger than something squared minus 4. So here you're going to have n squared minus 4 is equal to 1. And if n squared minus 4 is equal to 1, then n squared equals 5. And then you're like, oh, wait, you don't have a positive integer that you can square to make 5. Root 5 is not, it's not an integer. It's not even a rational number. And, you can prove that by other similar methods of contradiction and stuff, but you know that root 5 is not an integer because there's no integer which squares to make 5. I guess the easiest way to kind of check that would be to say, well, the integers, the squaring function is an increasing function. So if I do 2 squared and that's 4, and then I do 3 squared and that's 9, you know there's not an integer between 2 and 3. So there can't be the square root of a positive number between 4 and 9. And 5 is between 4 and 9. So that doesn't work. So here you have n squared equals 5, like no, contradiction. Sometimes when we have a contradiction, we draw this big fancy cross, which means no, it's stupid.
I've seen other symbols too.
Yeah, I quite like the cross because it's a very definite ending. Like, no, I say no, that's wrong. Anyway, so that's a proof. We've shown that there are no primes of that form because you'd have to have n squared equals 5, which is a contradiction. And then a slightly different way to do it, the other thing I thought of was, well, when you have n squared plus 4 times n squared minus 4, you could use difference of two squares again, and then you'd have n squared plus 4 and leaving it as it is, but the second one you could have n plus 2, n minus 2, because 4 is also a square number. And then...
So now it's looking suspicious because it's got 3 brackets.
Yeah.
And
it's
then really not prime.
I know that I then solved a quadratic, but I'm trying to remember my motivation.
Oh. Did you want 2 of these things to be equal to the number 1?
Yeah.
Oh, that's yeah, okay, that's quite exciting.
Basically, 2 of them have to be... Yeah, oh yeah, that's what I was going to say. Prime numbers only have 2 Yeah. So prime numbers only have 2 factors. So you know that basically 2 of these numbers must be equal. So I set 2 of them equal, and then I solved it, and the equation had no real roots.
Fair. I guess we could do something like you did before, where you say, "Oh, one of these things should probably be the number 1 if this is a problem."
Yeah, that works too. Basically,
that leads you to...
you know the smallest.
The same answer, right?
Yeah, you know the smallest of them. Oh yeah, so you know the smallest. Oh yeah, I remember. So the smallest of them is n minus 2, because n plus 2 must be bigger, and n squared plus 4 must be bigger than that. So if n minus 2 is 1, then n is 3.
Yeah. I saw someone in chat claiming that this is an example of this one gives a prime. In fact, this one doesn't give a prime because this one is 81 minus 16. 81 minus 16 is 65. Which is
not prime.
It's not prime because it's a multiple of 13.
Yeah. So that would be the only way you could have it, and then you can't have it, so you can't have any.
Yeah, RAF. Okay, yeah. So there's some subtlety going on. People in chat have got slightly different ways of phrasing this. Maybe this is a good point to talk about this. I don't know. Let's read out Raf's comment. Raf says, "I solved it just like this, and said that 2 of the factors can't be 1 at the same time. Is that enough?" Now, there's a claim in there that you can't have 2 of these things being equal to 1. I think this is where Flora's quadratic comes in, because is it obvious? We can have a debate, I guess. Is it obvious that if the first thing is 1 and also the second thing is 1, then that's impossible? You know, they're different expressions. They could coincidentally be 1, even though they're different expressions.
Except that is where the quadratic comes in.
Right, okay, they're not.
Because if you say n squared plus 4 equals n plus 2, then the quadratic that you get to solve is n squared minus n plus 2 equals 0. And that has no real roots.
Oh, okay. Fancy.
So basically, if that was equal to that, like if the first 2 factors were equal, then like they can't be equal. They can't ever be equal for any value of n. So you know that.
Okay, if they're equal because they're both equal to the number 1, then you could. Yes. I agree. You could write down that quadratic.
Because if they could both be equal to 1, then you'd think that if you set them equal, then when you solved it, you would get a root of 1, but there are no real roots.
Yeah. Okay.
Cool.
Arguing aside, this thing doesn't actually give you any primes at all. Not even for the small number 3.
No.
In fact, there's a fun fact hiding in this question. That whenever you work out this for values of n, n is 1, 2, 3, 4, 5, and so on. This is always a multiple of 5. Which you can prove. Well, you can prove in lots of different ways, like the odds and evens stuff. You can prove this is always a multiple of 5. Or you can use something called Fermat's Little Theorem, which is not on A-level mathematics, but is on university adverts. So this is an advert.
Yeah, I've done it at uni.
Yeah, Fermat's Little Theorem can tell you that that's always a multiple of 5. Fun. Okay.
Cool. So, moving on. I was going to go over to the left, maybe, so I can get more space.
Oh, right, okay, sorry. Yep.
It's fine. There's lots of nice space on the left. So I'm going to go down to this one. Prove that the nth root of 2 is irrational for n greater than 1, n is a whole number. So some of you may have seen a proof similar to this before, but what I'm going to go for is something quite similar. So I'm going to say, suppose not. So this is how people often start a proof by contradiction. Like, so suppose the nth root of 2 is rational. And if the nth root of 2 is rational, then you can write it as p over q, where p and q are both integers. And I'm going to also specify, and I'm allowed to do this, I'm also going to specify that p and q do not have any common factors. So whenever you have a fraction, if something can be written as a fraction, it can be simplified to its lowest form, where the top and the bottom don't have any common factors and you can't simplify it anymore. So I'm just going to assume that we've already simplified it. So p and q are coprime, which means they don't have any factors in common. The highest common factor of p and q is 1, if you like. And then basically I'm going to put both sides to the power of n. Anyone who might be stressed about that can satisfy themselves with the fact that both sides are positive. Oh, yeah, they are. So then you have 2. If you do the nth root of n to the power, nth root of 2 to the power of n, you get 2 back out. And then you have p to the n over q to the n. I'm going to multiply it up, so I have 2q to the n equals p to the n. And then what we can say is that p to the n is like 2 times q to the n, and yeah, so basically you have to kind of look at this and think about what the factors of each side are. And p to the n is 2q to the n, so p to the n can't have any factors that q to the n doesn't have apart from 2. It's like they have the same factorisation apart from the 2. So then, but because we know that p and q don't have any common factors, so remember when I assumed that the HCF of p and q is 1, I assumed I should have written that down because it's quite important. So p and q don't have any common factors. So basically this means that like whatever factors p has, q can't be a factor of p, because then the highest common factor would be q instead of 1. But we know the highest common factor is 1, so basically this means that q has to be 1. Because if q was anything other than 1, then it would be the highest common factor of p and q. So q has to be 1 here. And then in this situation, if q is 1, well then 1 to the n is always 1, regardless of what n is. So then p to the n equals 2. So then what you have is, okay, I have a positive number to the power of n equals 2. So basically the nth root of 2 can only be irrational if we have a whole number to the n equals 2. I mean, can only be rational, not irrational. If I said irrational, that was wrong. So it can only be rational if it's actually a whole number. And we know that the nth root of 2 is not a whole number for anything which is like n greater than 1. And well, how do we know that? Because the only whole numbers it could possibly be, well, it can't be 0, because 0 to the power of anything is 0. It can't be 1, because 1 to the power of anything is 1. And then, oh, that was an accident. It can't be 2, because 2 to the 1 is 2. 2 to the anything else, bigger than 1. Like 2 to the any other positive integer is bigger than 2. So it can't be equal to 2 if it's bigger than 2. And then the only other integers available to you are like 3, 4, and so on. And they're bigger than 2. So if you raise them to a positive power, they're not going to get smaller. They're only going to get bigger. So the only possible way this could work out and be true is if n is 1. But if you read the question carefully, it says n is greater than 1, which means there's a contradiction.
Right. I wonder whether... I like it. I like the bit with the highest common factor and the state saying therefore q is 1 is actually quite subtle.
Yeah, the q is 1 bit is tricky.
Yeah, I wonder if it's what people at home wrote as well. Let us know in chat. Well, so someone said, why did q have to be equal to 1? Which I think of sign of somebody not doing it this way at home.
Okay, I can kind of try and go through that.
I can think of other approaches as well.
Yeah, I could go back through it because basically, you know that q is a factor of p to the n. Q is a factor of p to the n, whichever way you look at it. And because p is q is not supposed to be a factor of p, and
right. So that's, I guess, where this is coming down to. And then you've got this kind of spare leftover case that maybe q could be 1, but that's somehow not important. The important meaty idea, I suppose. Am I allowed to say meaty for like the main idea?
Yeah.
The important main. It's not very vegetarian friendly. The important main idea is that. In this line, q is a factor of p to the n, but q is really not supposed to be a factor of p because this fraction was supposed to be written in lowest terms up at the start.
Yeah. I just realised the important fact is that if the HCF of P and Q is 1, then the HCF of P to the N and Q is also 1. That's like the important fact here.
Okay. Yeah. People in chat are talking a little bit about the proof that root 2 is rational, which they might have seen at school, which takes a different route at about this point, I suppose.
Yeah.
And goes down at this stage. You get an equation like this, which I think is uncontroversial in chat. That you can raise both sides to the power of n and rearrange it like this, and then says, actually, maybe I want this star further down. After this line. Oh, look at Miro being good at stuff. Okay. After this line, say this means that p to the n is even, and then to talk about multiples of 2. That's like what the proof for root 2 that you maybe learn in school is like. Say this means p to the n is even, and then a bit of work later. You say, well, you do a little bit of work and you say, aha, so p is even, and then you plug that back in, and it turns out that q is even as well. And there's ... here for do some work, but I think this is kind of the direction, the kind of finding a fact about the highest common factor. It's sort of secretly all the same thing, right? You're secretly finding a fact about the highest common factor. In particular, you're looking at multiples of 2. So people were saying, 2 somewhere, someone with the username 6n plus or minus 1, which is brilliant, says that Pn is even, so it has 2 somewhere in its prime factorisation. So P is also even. That's an example of doing this first ... of the work. Thank you.
Yes.
So this has got something going on like that. And this is how the proof that root 2 is rational works, the one that you see in school probably.
Yeah.
It kind of also works, I think. Sort of branches off at this star point to say, well, this is even, so P's even, so Q's even. Oh, but hang on, earlier up we said it was in the lowest common terms, and now we've shown it's both even. Okay.
Yeah.
Different roots are the same thing depending on how you feel about highest common factors.
Yes.
Cool. People in chat really, really want to know how hard the MAT 2021 is, and I'm not telling them.
How can you say,
I have
really?
to say that out loud, because people watching the replay can see people asking in chat, so I need to be really clear that I'm not telling them in chat. So, don't worry.
Yeah, good point.
Good, cool. Right, okay. Do you want to prove this thing about primes?
Yes,
in
I do. The final warm-up question that we're going to look at.
Okay.
It may look complicated, but it's actually kind of really quick. So,
I like that.
if you're surprised by this at this point, well, don't be. I'm going to use difference of 2 squares, everyone. Proof for any prime p that's bigger than 4. P squared minus 1 is a multiple of 24. So I'm kind of going over to the right again, you probably guessed. P squared minus 1 is equal to P plus 1, P minus 1. That's right. So then you have, okay, I've written P squared minus 1 as a product of 2 things. So these are factors of it. And if you read the revision, then you will know that one of, like for any number n, which is an integer, one of 3n, no, I've kind of started that wrong. One of n plus 1, and n plus 2 must be a multiple of 3. And you may be thinking, how does she know that? Well, if you think about it, you have a multiple of 3 every 3 numbers that you go along. So if you think about some actual numbers, like, so say I pick 7, you're like, well, that's not a multiple of 3. But if I go up 2, then I hit a multiple of 3. And then if you had, like, 42, that is a multiple of 3. But if you basically get any number, if it's a multiple of 3, then you're good. And if it's not a multiple of 3, you can only ever have to go up by 1 or up by 2 to get to a multiple of 3, because by definition, you have a multiple of 3 every 3 numbers. Hopefully that makes sense. Because that is my justification for why one of these numbers, p minus 1, and p plus 1 has to be a multiple of 3. And it's because basically if none of them were a multiple of 3, well, that would be a lie, because you have to have one every 3. And these are 3 numbers which are like consecutive. So you have p minus 1, p plus 1. One of them has to be a multiple of 3, and exactly one of them. So once I've justified that, you can look at it and say, okay, go back to the question. P is a prime that's bigger than 4. So p can't be a prime bigger than 4 and be a multiple of 3. That would be a lie, because it's bigger than 4 and it's a prime. So its only factors are 1 and itself is bigger than 3. So here you know that it can't be p. So one of p minus 1 and p plus 1 has to be a multiple of 3. It doesn't actually matter which one it is, you just know that one of them is a multiple of 3. Because these multiply to make p squared minus 1, you know that p squared minus 1 is a multiple of 3, because if something has a factor of 3 and you times it by something else, it still has a factor of 3. As long as, obviously, something else was a whole number. And then the other thing that we have is, p is a prime that's bigger than 4. Are there any even primes? Yes, there are, but there's only one. The only even prime is 2. So if p is a prime that's bigger than 4, then you know it must be an odd number. And hopefully you all know how odd and even numbers work. And if you have one more or one less than an odd number, it has to be even. Which means that p plus 1 and p plus 2 are both multiples of 2. I may have gone off the screen there. Of 2. They're both multiples of 2. Because they're both even. Because p is odd. So p minus 1 must be even and p plus 1 must be even. So then you have a factor of 2, and you have a factor of 2, and you have a factor of 3.
Doing good. So
and then the other thing, the final thing, I was going to say the final thing I need to mention, I was like 3 times 2 times 2, wait, 3 times 4 is 12.
It's the hardest bit of the question, we've got to work out 2 times 3 times 4, everyone.
No, the final thing I have to mention is, they are both multiples of 2, and if you have 2 multiples of 2, which are 2 apart from each other, one of them has to be a multiple of 4. That's because multiples of 4 happen like every other multiple of 2. Think about it, you go 2, 4, 6, 8,
right.
10, 12. Like every other multiple of 2, they alternate. Every other multiple of 2 is a multiple of 4. So either p minus 1 or p plus 1 must be a multiple of 4. So then you have 1 multiple of 4. And then you have 2 times 3 times 4. And then happy days, everyone, that's 24. So you know that you have factors within this expression which make 24. So p squared minus 1 is a multiple of 24.
Nice. It's a really good fact.
Yeah, these sneaky little number theory facts are actually really useful.
I like the way you use 2 facts about the prime. You use the fact that it's odd, it's not a multiple of 2, and you use the fact that it's a multiple of 3.
Yes.
And you combine those together to just say perfect facts about p plus 1 times p minus 1. It's very neat and tidy. Good. Okay. People are asking admissions questions, which I'm going to do later on, I suppose, because I want to talk about some math questions. And people have also very kindly pointed out typos. I'm sorry, there were at least 2 typos this week. If you downloaded the question sheet before Thursday, they were both fixed on Thursday, but that's probably a bit too late for actually fixing things. If you wanted to print it all out, correct version is currently on the website, I hope.
Yes.
Cool. Can you prove the 4? Yeah, you can prove the 4 algebraically, if you like.
Yeah.
By writing the p plus 1 as 2k. Yeah, I like that. So if you write it as 2k, then the other one will be something like, 2. If one of them is 2k, then the other one will be maybe 2k minus 2, perhaps.
Yeah.
Because how they've written it there in chat.
Yeah.
And then 2k times 2k minus 2 is 4 times k minus 1. And then you argue that k times k minus 1. Aha, that's 2 consecutive numbers. One of those is even, k or k minus 1. So there's another, we can squeeze another factor of 2 out of this. I like this, it's very efficient. Good, okay. Other number theory facts, says Jack. I don't think the number theory facts that we're doing here today, I'm really doing as an example of doing stuff with prime numbers and doing stuff where you prove things. We're proving this fact for all primes. This is, I guess, the combination of proving things and about primes. You're not really expected to know specific facts about prime numbers. I mentioned Fermat's little theorem in passing earlier. You're not expected to know what Fermat's little theorem is. Somebody told me it's in further pure maths or something. So if you're doing further mathematics, then you might learn about Fermat's little theorem. If you do maths at university, you will learn about Fermat's little theorem. But the actual content of like knowing things about powers of primes is not necessary.
Yeah, I think you don't have to know that these things are true. You just have to be able to think of tricks to figure out how to prove them. And the more practice questions you do, the easier you'll find it to figure out, like, oh, I can use a trick about odd and even numbers. Like, you've probably hopefully seen by now, there's always a trick where you can say, you're proving a fact for all positive integers. You can prove it for numbers which are of the form 2n and numbers of the form 2n plus 1. And that's because every number is odd or even. So it's just little facts like that. Like, you know, every 3 numbers has a multiple of 3. You just use what you already know from kind of basic maths, and then you put that into a proof context.
That said, if Jack, if you do want to learn more about number theory, then there are some really good UKMT resources, which somebody reminded me of this in chat. SV has reminded me in chat that the UKMT's got good resources about prime numbers, and there's just quite a lot of stuff. I think people who have to do the International Maths Olympiad sort of stuff have to learn facts about prime numbers. So there's lots of resources out there. Art of Problem Solving has got lots of very advanced facts about prime numbers, for example. There's loads of stuff out there if you want to go and read it. I'm not saying you need to understand this question that's on the screen now. Which has the word prime in here. Yeah, did you like that transition to the math question?
Loved it.
Working on my segues.
I like this question.
One day I'll do a segue without commenting on the segue itself. Right, here's how the question works. It describes a process. This is the opening of the 2015 paper. It describes this process. It says pick a whole number, and for a moment you think, oh my word, I've opened the test paper and it's asking me to do a magic trick. Add 1 to your number, square it, multiply by 4, subtract 3, and then it'd be really good if I'd really like it if the question stopped there and the options were, what's your number? And magically we'd got it. Never mind. That would not be a good math question. Here's what we're asked. We're presented with 5 statements. They're given Roman numerals, and we're asked which ones of these statements are true, regardless of which starting number is chosen. Regardless here means that no matter what starting number you choose, starting whole number I suppose, no matter which starting whole number you choose, some of these facts will be always true about the output. People would like a poll because they've started having a go at the question. Let's turn on the poll, because why not? The poll's got 5 options. The poll's got A, B, C, D, E options. Here it's slightly awkward. A, B, C, D and E corresponds to different combinations of the 5 statements. Roman numerals. It's one of those ones where really you don't want 5 options. Really you want 32 options for what you might believe about the truth or not of each of these statements. 32 because it's 2 to the power of 5. Unfortunately, the English alphabet doesn't have 32 letters in, so that'd be pretty tricky. The poll is going pretty well at the moment. People are pretty strong agreement. I've hidden the results, which makes this not great content for the video, but it's fun for me. I can see behind the scenes. Yeah. I think Flora can too, right?
Yeah, I can.
Oh yeah, no, brilliant. Right, we're having a lovely time.
Exactly.
Answer to this question. Let's start trying some numbers, I think. When I see a process like this, I'm going to pick a whole number. I'm going to be cheeky. I'm going to pick the number 0. Am I allowed to do that? Yeah, I think I am. I'm going to add 1. I'm going to square the answer. You see, picking small numbers is nice like this. 1 times 1 is 1. Welcome to the Oxford MAT Livestream, brought to you by the University of Oxford. Multiply by 4 and subtract 3, and I get back to 1. Okay, cool. So, quick check. Final answer is odd. It's currently true. I'm not saying that's true for all numbers, but it's true so far. Final answer is 1 more than a multiple of 3. That's true. 0 is a multiple of 3. It's 0 times 3. Yes. 0 is a multiple of 3. 1 more than a multiple of 8. That's also true. That's not prime. True. Spooky. How did they know? And it's not 1 less than a multiple of 3. That's also true. Okay, so I currently believe that all of these facts could be true. What do you think at home? Let us know in chat. Did you try other numbers? Did you get other answers? Can we work out which ones of these facts, which facts are true? Maybe we could keep checking different input numbers. So this is my input. Or maybe we can be a bit cleverer. Becca likes this question, which is nice.
Yeah,
Becca,
it's good to hear.
It's always a toss up between. Hang on, I worked out how to do this once.
Put the poll in the chat.
The poll running, but chat on screen, because chat is now being clever and talking about the question. If I zoom all the way out and go, oh, show Q&A, and then I can zoom back in again. What is this, episode 9? Oh, we're finally working out how to use technology. Trying 1, 2, and 3, says somebody in
Gets you
chat.
pretty far.
Pretty far.
Someone whose
How many
name
numbers
is
should you try, says Emily.
Microbatic.
Which is a good question. I would try a couple. I'd try probably 2 or 3 before I got bored.
Someone suggested it might be faster to write an equation first.
Oh my word.
It's a good idea, not gonna lie.
Maybe using some sort of algebra, right? But if I put in my input n, and then I'll get n plus 1, and then n plus 1 squared, 4n plus 1 squared, and then 4n plus 1 squared minus 3. Oh, brilliant stuff. I kind of want to multiply that out, I think, just to see what happens. What's that? 2n in the middle, so write down 8n plus 1 at the end. Okay. That's looking like 1 more than a multiple of 4, but that's not an option. So, shame. That is odd though, isn't it? This bit's even, because it's definitely a multiple of 2.
Yes.
This is odd. I think 1 is true.
So we have figured out that 1 is definitely true.
Yeah, I think this is odd. Algebra for the win. Okay.
Yeah.
Somebody says in chat, easy as a ruler, options maybe. Okay, so I want to not pick C, I think, because C doesn't include this fact I've just proved, that things are always odd. Okay, good. I'm a bit stuck now. I want to think about multiples of... What do I want to think about? Multiples of 8, maybe? So I've got this multiple of 8 in here. 1 more than a multiple of 8. What am I doing here? I could write this... So I'm a bit suspicious about whether this is a multiple of 8 or not. I can see this bit is a multiple of 8 in the middle, because I've got a plus 1. I'm a bit worried about whether this 4n squared is a multiple of 8 or not. I sort of think maybe if I take n equals 1... I was calculating n equals 1 before. Hang on, right, let's keep going with 1. 16, and then subtract 3. 12. Oh my word. 13. Oh my word. That's a new low, isn't it? 13 is not 1 more than a multiple of 8. This is false. Okay, so back to Emily's question. How many values would you check? Checking 1 would have been a really good idea, and I should have finished off that calculation. I also got a chance to think of it here in this kind of algebra expression, because I was thinking about whether 4n squared is a multiple of 8 or not. I was thinking, it's a multiple of 4, but then is it a multiple of 8? That's a bit like asking whether n squared is even or not, so I should check an odd number in here.
Yeah, so someone's just given us a counter example.
Oh, right.
4n squared is not always a multiple of 8. For example, n equals 3. It isn't.
True, right. Okay, n equals 3. And that also works if you follow through the calculation through here, because this turns out to be not 1 more than a multiple of 8 as well, and when n is 3. Okay. Somebody in chat says quadratic residues mod 8. I think if you know about quadratic residues, then this question is probably not very hard for you.
I was going to say, if you know about quadratic residues, I'm impressed.
And if you don't know about quadratic residues, then that comment's not very helpful to you. So
yeah, no, I didn't study that
between.
until uni. That is some higher level number theory. Don't worry about it.
There is a Oxford Online Maths Club episode about quadratic residues. I think it might even be the first one, or possibly the second one I did.
Yeah, near the start.
January this year. Before I had any guests on or anything. Anyway, right, cool. Where are we going? 3's not true, so I think not this one either. Doing pretty well. I've got down to 1's true. I need to decide whether 2, 4, or 5 are true. Should I think about 2? Yeah, people are helping out in chat or commenting that I can't do subtraction, which is nice.
Bit harsh.
Let's think about 2. Is this 1 more than a multiple of 3? That's a bit like asking, is this 4n squared plus 8n, is that a multiple of 3? Doesn't really look like a multiple of 3, does it? I guess it's like, I sort of want to factorise it again a little bit, but there's all these 1 more in the thing.
Yeah.
One more than makes me want to ignore the one more than and talk about this thing over here. Like that. Does that make sense? Because then I'll put the plus 1 back in as well. Okay. Because then, if you want to know, is this 1 more than a multiple of 3? That's like asking, is this first bit a multiple of 3?
Yeah.
And I think that's pretty clearly not always a multiple of 3. It's got a weak spot, right? That it's a multiple of 3 if n is a multiple of 3. It's a multiple of 3 if n plus 2 is a multiple of 3. Which is not quite all the numbers, because what if n plus 1 is a multiple of 3? For example,
Then you know that.
Then you know maybe this is not going to be a multiple of 3. For example, n is 2. Now maybe I should check some small numbers. The person who said checking small numbers is looking pretty prophetic right now. 4 times 9 is 36. Subtract 3 is 33. That is not 1 more than a multiple of 3, is it? Cool. Yes. Oh, and someone's just put that in chat as well. Thank you to the anonymous person who put that in chat at the same time that I was writing it. Cool. Good. Okay, so not this one either. Is that we done? Not quite done. We've still got 4 and 5 to think about. Apparently, exactly one of these facts is true. Wait, hang on. So this 4 thing, the final answer is not prime. Isn't that just false because we got the number 13 out for one of them? Hang on, have we accidentally done enough work for this one? I don't really want to think about whether this expression is prime or not. Seems really tricky.
Yeah.
But hang on a minute, we got the number 13, and this says not prime. So I think this is false. Which eliminates B. So I'm left with option E. And I suppose 5 is true. Should we try and prove 5? Finish up 5. Oh yeah, people in chat telling me that 13 is prime. 13. Good.
5 can be disproven with n equals 1.
N equals 1.
Someone is saying that.
But that's an example of something that is
No,
that
it
is
can't.
not. Yeah, 13
Someone
is really
disagreed with
mind
them.
twisting.
It's not 1 less than a multiple of 3. 13 is not 1 less than a multiple of 3. Everyone, stay calm. It's all
So
good.
that's not a counterexample to this statement that the final answer is not 1 less than a multiple of 3. In fact, the final answer is not 1 less than a multiple of 3, which you can prove by thinking about multiples of 3 for the initial number. I don't really know if I want to do this, but you could think about plugging in the number 3k, or 3k plus 1, or 3k plus 2. If you plug those things in and run the process, then it turns out that whatever you pick, these are the 3 possibilities for what your number might look like when you plug it in. It's either a multiple of 3, 1 more, or 2 more. The final answer turns out to be, in all 3 cases, the final answer turns out to be not 1 less than a multiple of 3. So this is in fact true. Not proved on stream. Check the answer document. People in chat telling me lots of modular arithmetic mod 3 facts, but I think we got there by eliminating options. Cool, and I think chat agrees, right? Yeah, chat's at like 75%, which is pretty good. Let's have a quick look.
Yeah,
Oh,
75%.
What did people vote for? I always like looking at what people voted for if you didn't vote for the right answer, because we're here for learning things, right?
Mm-hmm.
Yeah, so people voted A as well, which is very similar, except for the binary bit of is 2 true or not. And some people voted for B, which is similar, except for the bit about 4 and 5. Okay, so I can sort of see how you'd vote for A. That comes down to 2, which is this odd argument about multiples of 3. You might, if you believe it is always 1 more than multiple of 3, well, I guess you needed to put 2 in. You needed to get up to numbers this large to see that sometimes, no, it is multiple of 3. Okay, good stuff. Thanks, chat. Good. Okay, how much time do you get for the MAT? You get 2.5 hours.
Mm-hmm.
Does this MAT question test whether you know how to plug in numbers? A little bit, and I nearly got that really badly wrong. A little bit, and also checking that you can understand like what these statements mean when you get the numbers out, which is quite a lot of maths, right? Can you decide whether things are true or not, given some facts about numbers? Okay. Oh, right. That was exciting, wasn't it? The whole chat just went off. Good. Okay. I've got another question that I'd like to do if Slido wants to play along. This one's quite a bit harder, and it's 5 to 6. What do we think? I'm going to come back to this. I'm going to do an audacious change of plan. I'm going to talk about this question instead, because I've put some long questions on the mat sheet. I'd like to talk about them. Last time I tried to speed run this thing. So here's a long question. It's got different parts to it. It's got prime numbers in here as well. I'm going to speed through the first couple of parts because I want to talk about part 3. No, part 4. I want to talk about part 4. So, spoilers, when you multiply this thing out in part 1, expand and simplify expression, this turns out to be, let's put this over here, this is equal to a to the n plus 1 minus b to the n plus 1. It's a fantastic fact. It's a really good, it's like difference of two squares, but wow, enormous. Part B was in the warm-up. That's about thinking about n squared minus 1. And part 3 is very similar. You have one more than a cube number would be n cubed plus 1. Can that be a prime number? N cubed plus 1. We'll need a way to factorise n cubed plus 1, I suppose, perhaps. Or if we had something like that, then we could make a statement about this. In fact, this factorises really nicely. I don't really know if people know this, but because if you put the number minus 1 in, you get 0, because minus 1 cubed is minus 1, plus 1 is 0. So this has to factorise, as a polynomial, this has to factorise with n plus 1 as one of the factors, because minus 1 is a root of that polynomial. Factor theorem from last week. Yeah, factor theorem.
Some point.
N plus 1 has to be something like this. So this has to factorise a little bit, and then I can do some polynomial division to work it out. Okay. And in fact, this looks like it's not a prime number. Good. Okay. Or alternatively, thank you, Payne in chat. Payne in chat says this is n cubed minus 1 cubed. So you could use the thing at the top of the question. Clever. I like it.
Yeah.
Bring all the minus signs inside. A equals n. B equals minus 1. Brilliant stuff. Okay. I want to talk about part 4. Yeah. Oh, okay. People in chat are telling me to use part 1. Using previous parts of the question.
Very important.
This is the same fact, right? Okay, good stuff. So, part 4 of this question is fun. It says, this question's from 2015. Is 3 to the power of 2015 minus 2 to the power of 2015 a prime number? You should really, really not try to work out this number. It's very big. Explain your reasoning carefully. That sentence is in there so that you don't just say, nope, and walk away from the question. Because it's important to explain your reasoning here carefully, because it's possible to get too excited and to spot. Yep. Okay. To spot that. Okay. This is not divisible by 3 or 2. Good start. Only infinitely many more prime numbers to check, I guess. But we can stop when we get to this number, I guess. Anyway, it's easy to get overexcited and spot that this looks like the same format as part 1 of the question. This looks like an a to the n minus 1, n plus 1 minus b to the n plus 1. So actually we can factorise this number. We can write a equals 3, b equals 2, and n is 2014. And then we'll get some factorisation that starts a minus b times 3 to the n plus 3 to the n minus 1b plus ... plus some huge number at the end here, 2 to the 2014. That's really exciting because I factorised the number. Yeah, so an anonymous person in chat has also typed that out. Thank you, anonymous person in chat.
Yeah.
What's the problem?
Anyone who's read the hint might realise the problem.
Oh, bother, I've put it in the hint again. I should read my own hints.
It's okay.
Yeah, it's in there.
Even prime numbers are allowed to be a multiple of 1.
Even primes are allowed to be a number of 1. And also the odd primes are allowed to be a multiple of 1. Right, this is 1 over here. Yeah, okay. So even if this is a prime number, then we haven't proved it's not a prime. And that's a really weird thing for me to say, right? We haven't proved it's not a prime.
Indeed.
Because in fact it's not a prime. We're going to factorise it in a moment. But with what I've currently written, we haven't proved that it's not a prime. It's a weird state to be in. Okay, there's a trick which I've seen some people in chat. The username E. I don't know if you were first, but somebody else has also pointed that out. That we can use other numbers, maybe 4 and 9, or different powers. Oh, Rebecca's got some n equals 2013 stuff. Oh, let's think about this. So 2013, but you take out a power of a squared minus b squared. That is tricky, I think, because taking out a factor of a squared minus b squared out the front, I'm a bit scared. I'm a bit nervous of all of these terms inside. I'm a bit worried about whether they all work. Up in part 1, we proved this fact with a minus b. I'm a bit scared about pulling out a factor of a squared minus b squared. Why am I scared?
Yeah.
Am I right to be scared? Maybe I'm just wrong to be scared. Does it all just work? If you write down a new factor, you skip in 2s each time. I guess that works if the number is even, or maybe only if it's odd. Hard to think straight. You need a new version of the fact at the top, Rebecca. Other people have got suggestions.
Someone suggested use a as 3 to the 5 and b as 2 to the 5.
Nice, I like it. So this one is less thinking, which is the reason I'm writing it on the screen. Rebecca's suggestion, I'm not sure whether it works or not, which is the only reason I'm not writing on the screen. It's possible it works. You just saw me fail to subtract 3 from 16. Tricky thinking is probably not where I should be right now. This is like comfort food, right? It's just... brilliant. Okay, we can write down this fact. 2015 is not prime, it's a multiple of 403. And that means we can write down this fact. We're asked about this number, and now it looks like a to the n plus 1, b to the n plus 1 with different values of n, but importantly, different values of a and b. So we get out this factor, 3 to the 5 minus 2 to the 5, times all manner of junk. And this is not 1, so this is not a prime number.
Indeed.
Because it's got this factor over here. Cool. Okay.
Great.
Did we do this last week? We did something with a cube. We did there was a picture of a cube. I was going
to say, it wasn't this question, but it was some cubes.
Pretty similar. Good, right, okay. We could also use other numbers. People know other factors of 2015, which is quite
2
exciting.
to the 13 and 2 to the 13, but that seems excessive.
Yeah, people are doing the last part as well. Bounding it between two... somebody told me about bounding things between two successive cube numbers last week. Okay. Cool stuff. What are we doing next? It's about 6 o'clock. I understand people have got to go if they've got to go, but there's like 100 people here still right now.
Wow.
Let's do a really
I'll
quick
go in like 10 more minutes.
You're going to go in 10 minutes? Okay.
What a great question. Will we lose marks for multiplying by junk in the test?
So...
Potentially you may not write junk in the exam, but you could write, a positive integer.
I'd give it a name. If I wrote J for some integer, for some whole number or integer or whatever, J. I'm trying to say whole number instead of integer because I think it's more friendly to say whole number, but sure, for some integer J, then that's pretty much the same. Giving things names is really important. I like giving things like names, like calling it junk or just drawing a big rectangle with a squirrel in it, but yeah, giving things names is really powerful. Cool. I'll put a poll on. See what people want to do. There were some questions that came in before. Adam's asked a complicated question about cosine rules.
Yeah, I'd start that. Maybe it's one for later.
Might be one for later. Adam, it's possible that the question's wrong. I guess it's possible that the solution on the web's wrong. It's possible that the inverse cosine function is just really weird. I'm going to read your comment properly when we're not live and type you a response afterwards. I do that sometimes. I come back afterwards.
Yeah.
sometimes. Somebody's asked for my favourite Oxford college, which is not fair because I love all the colleges.
Oh, I have a favourite college, but that I'm allowed to because I go to one still.
Ah. I think previously I said my favourite college is the one to most recently pay me to do a thing, but that might have sounded a bit like soliciting bribes, so I'm gonna move on from that. People are voting, so it's surprising that people are voting and still here. People want to do another long question, or maybe they want to do the last part of that long question for a fresh change. The other long question is there, and we've spoiled the best bit of reusing the previous part of the question, which is good. For a change, let's have a different Matt long question. If we just write ... Yeah, I'm fine with ... I think it's always good.
Yeah.
It's like I usually say about writing little bits of words to explain something.
Yeah, you can always write a little arrow and explain what you mean.
The brackets are kind of the important part, right? Because you're saying there's something here, but it's multiplied
Something.
by the other thing. I guess this is good if the scenario is that you're literally running out of time to the point where you can't write the word junk. Right, okay. I'll do the gap year question in a minute. Here's another Matt Long question. You voted for this. So this question is here to introduce some new mathematics. I didn't have a space for it in the other parts of the Matt Livestream, so it's here. Digit sums. Do you remember those? Here, the digit sum is what you get when you add up all the digits. We've got a definition, we've got an example. Importantly, there's a separate thing, I can't remember what it's called, possibly the digital root, where you keep doing that. You keep working out the sum again and again and again until you get down to a one-digit number. That's not what this is. This just says sum the digits, i.e. just do it once. I think it's this trick for checking whether things are a multiple of 3 or 9, where you keep adding, you keep going. Okay. Oh yeah, wow, somebody's put that in chat in capital letters. Brilliant stuff. I can read that from here. Right, okay. Here's the question. How many positive integers, this question does say integer. Integer means whole number here. Less than 100, so 2 digits, or 1 digit, I suppose, have a digit sum equal to 8. Okay, that's a question. We can have a go at that, I suppose. How many different ways are there to make a digit sum of 8 using a 2-digit number? And I see someone's put something in chat that I thought was a string of numbers, but it's actually a list of... Well, it's a list of... It's not the numbers from Lost, it's the numbers with digit sum 8. I think there are 10 of these. SV would like a poll. The polls are actually annoying to make on the fly with possible answers for long questions.
I was going to say, can I try and create a poll?
Do you want to try and create a poll for part 4? Do you know the answer for part 4? I've got it on a post-it note on my monitor.
I don't know what's going on, never mind.
Never mind. Okay, right. We're not going to do a poll. We're just coordinators not doing a poll. This turns out to be... First one here is there are... how many of these are there? I suppose there are... Well, okay, so the first digit could be 0, 1, 2, 3, or so on up to 8. Could be 8. And then the second digit has to be whatever you need to add up to that to make the digit sum be 8. This feels a little bit more like killer Sudoku or something rather than maths, I think. So I think I've got 9 possibilities. I can have basically any first digit I like except 9, and then I can put another number in there. It's possible that if you're counting these and you've got 8, then you're possibly missing... Yeah, so it's weird. We're adding up to make 8, but there are 9 possibilities because don't forget about 0 in this game. That the number 80 is allowed and the number 8 is allowed. Here's a number with digits sum equal to 8. 8. Okay. So slightly wonky start to the question, which I had to think about digit sums and remember that 0 exists. Let's try and list them. I'm going to list them over here. 17, 26, 35, 44, 53, come on, 62, 71, 80, right, cool. Second part of the question, what if the digit sum is equal to n instead, where n is some positive integer less than 10? So we know the answer when n is 8, now we're asked for other ones. Somebody in chat says 0 to 8 for this number at the top. Brilliant, I love it. And I suppose, what do we need to do for this? Wow, people are thinking about 9 choose 1. 9 choose 1 is popular with some anonymous people. If you think about a string of cards, you've got to place a divider in. I guess, are we placing a divider in? What's the divider have to do with the digit sum, right? We need to make sure that the digits add up. What if n's not 9? I think, or yeah, what if n is 1? If n is 1, then the digit sum can only be if n equals 1, then the digit sum is 1. So I'm going to have to be stuck to be using the numbers 1. Or I could use a 0, I suppose, or 10, but I'm going to be less than 100, so only 1 or 2 digits. So my answer would be 2. And in fact, thinking about it like this, working systematically through the possible first digits, here I was making the digit sum of 8, and there were 9 possibilities for what I wrote down for the first thing. Here, if I'm making the digit sum equal to n is quite small, there are n plus 1 possibilities for what that first digit could be. And then you fix it with the second digit. Okay. People in the chat seem to agree, n plus 1. Good question. Do you have to put a written explanation? The way the question's phrased, it's not quite clear. I would write down a written explanation, I think.
It's best.
I think I would explain that. Just in like one line, one sentence, n plus 1, because of the possible first digits, or something, even vague like that. Yeah, so here we're thinking logically about what the first digit could be in the different, it's sort of like looking at different cases. Each different case is pretty easy, because once you've decided that the first digit is 3, then there's only one possibility for the second digit. We're on 2-digit numbers. Part 3 is going to be more interesting, because part 3 wants us to think about 3-digit numbers, which it says positive integers less than 1,000. That means 3-digit numbers, or 2-digit numbers, or 1-digit number. Okay, we're still looking for ones with digit sum equal to n, where, let's remember, the digit sum, we just add the numbers together once. So, there are numbers in there with huge digit sum. The number 999 has digit sum 27, but we're just looking at numbers n less than 10. Okay. How vague can your explanation be?
It's hard to quantify, really.
Vague on that one as well. Sorry. If it's clear you know what you're talking about, then you usually get the marks. If it's not obvious that you know what you're talking about, or if you write something that's not true, I guess, then it's less likely you get marks. That was too vague to be useful. Sorry, Raf. Okay. Right, part 3. How many positive integers less than 1,000 have a digit sum equal to n? Where am I going to do this? I think I'm going to go over here. So maybe we should start by thinking about an example. Let's think about the digit sum 8. So I've got possible first digits. This is a 3-digit number I'm thinking about. If I include the zeros at the front, then all of them are 3-digit numbers, like 008, which is, I suppose, appropriate for today. Almost. I should have picked 7. Bother. 008 is kind of, your possible first digit could be a 0, or 1 or 2, or up to 8. So all these possibilities for what that first digit could be. Only up to 8 though, because if I make the first digits too big, then the digit sum's too large already. Aha, okay. So we've already seen that if the first digit is 0, then we're actually looking at numbers that are smaller than 100. So in that case, in that particular case, if the first digit is 0, then there are n plus 1 ways to continue. Okay. Oh, I've written n plus 1 where n is 8 for this example over here on the right, I suppose. Let's think about what happens if I write down a 1 to start with instead. So in this case, if I write down 1, then I've got 2 digits to go, and I want these two to have a digit sum of 7. Or in general, I suppose, n minus 1 if this was n at the top. I want them to have a digit sum that's 1 less. I've already used 1 of my digit sum allowance over here. The number of ways to make a digit sum of 7 with 2 digits, we said in the previous part, was what? m plus 1, where n is the number that's the digit sum we're going for. So in this slightly convoluted way, I think I've talked myself into saying that if I started with 0, then I've got n plus 1 ways to continue. Great news. If I use up one of them, then I've only got n ways to continue. I've got slightly fewer options. I've lost 1 because I've put a 1 down as the first digit. So I've lost 1, but then I get 1 back because there's this bonus option of using 0 for my second digit. Don't think about it like that. That's not a great way to think about it. Anyway, if I use 2, there's a pattern here. If I start with 2, then I want my next digits to sum to 6. There are 7 ways to do that, just n minus 2 ways to do it in general. And then if I start with 3, there are n minus 3 ways to continue, all the way down until if I start with 8, then there's only 1 way to continue. I've written down 8, my digit sum is going to be 8, so I'm going to have to write down 8, 0, 0. Or in general, n, 0, 0. Okay. What have I got? In total then, I've got, my total is n plus 1 plus n minus 1 plus ... plus 1, which is an arithmetic series. I can sum all of that up. That's something like triangle numbers or some sort of arithmetic progression where I can think about the first and last terms or the common difference. I get this number over here. Okay, brilliant. I've got some expression for this 3-digit number case where really the thing, if you take anything away from this, you don't have to, but if you take anything away from this, it's the way that I've decided to work systematically through the different cases. I've got all these arrows splitting off into different cases, thinking about, I'm going to think about what the first digit is, and then treat each of those separately, and then try and spot a pattern that I can then sum to add everything back up again.
I'm just going to take this moment to dip out and say goodbye.
Bye, Flora. Sorry, I just talked for 10 minutes straight.
It's fine, don't worry.
You've been managing chat really well.
Yes, I've been on chat. But I'll be here next week on chat again.
Yeah. Thanks, Flora.
Thanks. Bye.
Really bad. I just talked over Flora for the last 15 minutes. Whoops. Okay, right, I'm still here. We're gonna do, people say bye Flora. People saying bye Flora, loads of people saying bye Flora. Right, cool, okay. Good stuff. Whoops, I don't know what I just did. Oh my word. Flora's left and now I've broken everything. Okay, I think I'm still live. I think I'm still doing a MAT question. I think I'm still here. I think I'd like to think about, so there's this follow-up part of the question. The next part of the question is less exciting to me. I really like this big result we did. Later on, there's these questions about how many positive integers between 500 and 900. So that's restricting what the first digit is, restricting some of the cases, and also saying that the digit sum has to be 8. It's kind of less exciting to me, but you can work through that systematically by thinking about the first digit. Is it 5, 6, 7, 8, or 9? It can't be 9, so is it 5, 6, 7, 8? Think about those possibilities separately to get some sort of reduced sum, just for the case n equals 8. So that's somehow less exciting to me, and I figure I can probably have a go at that. There's not that many of them, right? The last part 5 here, let's see what other people are thinking about. Oh, also getting some spam. Maybe it's Flora on another account. Okay. There's this part about having at least one digit equal to 5 that I quite like as a follow-on. Let's pretend we've done part 4. And let's say we've done part 4 and we've found all of the numbers between 500 and 1000, not including 1000, 500 to 999 that have digit sum equal to 8. Let's pretend we've done that and we've got some number, we counted them, it was a lot of work. Can I have suggestions in chat about how you would do part 5? How would you work out how many numbers are there? And no restriction on what the first digit is, but you've got to have at least one of your digits. Sorry, you've got to have one of your digits at least 5. So one of your digits has got to be 5, 6, 7, 8. Okay. 6m plus minus 1 says they like part 6. Okay. Okay, suggestions in chat. So you could check by thinking about the different possibilities. I like this. The different possibilities of having a 5 in each place. I suppose it doesn't have to be exactly 5. It's really weirdly phrased, right? There are 2 English phrases that this could be. You've got to look very carefully to decide which one it is. It could be at least one digit equal to 5, or it could be at least one of the digits is at least equal to 5, or something like that. And if you look really closely, it says one digit at least 5, but it doesn't say which digit. So I suppose that means at least one of the digits is at least 5. Yeah, we already did the case. I like this. We already did the case where the first digit is at least 5, and then there's some sort of symmetry thing to switch them all around, to move them around. Yuki's here. Yuki says it was 10 for the previous part, so we can do some sort of switching them around thing to shuffle those digits that we got before, to see how many we get for the other digits. I quite like that. Does that work? I've suddenly become scared about repeated digits. Am I supposed to be scared about repeated digits? Maybe I am. So I was hoping you could just sort of multiply it up and get away with it, but now I'm a little bit worried about the difference between you know, all those combinations shuffling questions where you have things like this and things like this, and if you shuffle the digits then different things happen. But maybe we should think about the separate cases. So instead of shuffling the digits around, because that could be complicated depending on whether they're repeated digits, we could think about the 3 cases. Case 1, first digit big. Case 2, second digit. And case 3, third digit at least 5. And these are mutually exclusive, because you can't have 2 of these cases, otherwise your digit sum is absolutely huge. It would have to be about 10 or something big like that, which is not, digit sum is 8. Okay, yeah, just triple it. Brilliant. So someone said the word triple ages ago, and it got lost in a bit of spam, sorry. Yeah, I agree with Minty. I was saying, for a while I was saying at least one digit being about 5. There's Minty's comment. But only one of them can be 5. That's right. Okay. Wow. Okay. Since Flora left, I've got much worse at maths. It's quite notable, isn't it? Oh, there cannot be repeated digits. I think they can be repeated small digits. Cool. And Anonymous down there somewhere has listed the 10 possibilities of numbers with digit sum equal to 8 that are between 500 and 999. Yep, I think that's right. Good, right, 10 of them. Okay, so 10 here, and then each of these 3 cases, this is sloppy if I just say this out loud, but 3 cases, each of them there's 10 possibilities, so 30. Digit sum doesn't really care about order of your digits. Okay. Good, right, cool, okay. How much spam are we getting? It's not too bad. Okay, cool. Sorry if your comment is being held in Slido for quite a while. It's suddenly been hit with loads of spam. Fun. Okay. Last part of the question. What's the total of the digit sums? Somebody said this is the fun bit of the question. What happens if you add together all of these digit sums, which are themselves added together the digits of some numbers? What happens if you add it all up? Yeah, no. Okay. George, I've seen your edit. Good. Yeah, so people are talking about repeated digits. George has clarified that they meant a repeated 5, 6, 7, or 8. You can't have a repeated 5, 6, 7, or 8 because then the digit sum would be too big, which is what Minty said before as well, and what I eventually realised was true. Good. I think we all agree. You can have a repeated digit like 611, but you can't have a repeated 5, 6, 7, or 8 because that's too big. Cool. So there's this question. So there's this question about what happens when you add all of these together. So you take the digit sums of all of the numbers between 0 and 999. And my intuition for this is something like I'm adding together all of the digit sums of the 3-digit numbers between 0 and 999. That's going to sort of fairly treat all of the digits. It's not like if I stopped at 500, then the numbers 6, 7, 8, and 9, they're missing out a bit because I didn't check those large hundreds numbers, but I've got all the way up to 999. It's like rolling the tickers all the way around from 0 to 9. So it's going to be quite fair to all the numbers. So maybe I can do something that treats, all the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all going to turn up equally often, I suppose. And then I'm trying to think about what it means to turn up equally often. And that turns out to be a key to working out the answer to this question. What does it mean to, you're looking at all of the possible numbers. There's a lot of adding going on. We're adding together all the digits in all of the numbers between 0 and 999. So it's quite a big picture of what happens if you write down all of the numbers between 0 and 999. You put spaces in between all the digits, and then you put plus signs in all the spaces. We're going to do that some. Yeah, we write down each number. This is I agree with this intuition. I'm going to do the GCSE question in a minute once we've got to the punchline of this, I think, because we're near the end of this question. You'll get each digit the same number of times. I guess the question is, how many times do you get each digit? So how many times do you get each digit? How many 9s are there when you work this out? And I'm imagining these kind of tickers spinning around. So actually, I think they spend... It's sort of fair, right, between the digits. So it should be about 1/10 of them, right? There's 1,000 numbers there, and in each place, the units ticker, the units digit, just cycles through numbers. So that spends 1/10 of its time on 1, 1/10 of its time on 2, 1/10 of its time on 3. There's 100 numbers with units digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I'm going to get 100 from that units digit spinning around. I'm going to get 100 1s, 100 2s, 100 3s, 100 4s, one after the other, cycling through. Okay, so last digit is 9 100 times. Okay, people are doing good here. The other two digits are sort of the same story. They just go through the digits in a different order. They're also fair between these 10 digits that they could display. So it's also going to be 100 times from each of those as well. Let's think about I think the first digit is easier to think about, perhaps. The first digit is 9 100 times, and actually those all happen in a row. Right at the end, you go from 899 to 900, and then you hit 100 numbers in a row. 9000 up to 999, 100 numbers in a row that all start with 9. And also in between, the second digit is also 9 100 times. That's a little bit harder to think about with my mental model of ticking through all of the numbers. I'm imagining those like clicker things that tick the numbers up. This is a little bit harder to imagine because it does the 9s in patches of 10s. Maybe it's easier to think, well, it spends 1/10 of the time in each of the digit positions, so 100 times. Putting all that all together, that's 300 9s. We've also got 300 8s, 300 7s, 300 6s, 5, 4, 3, 2, 1. So our final answer for this sum of all the digits, sum of all the digits, is going to be 300, because that's how many times we see 9. We also see 8 300 times. We'll also get 6 and 5 and 4 and 3 and 2 and 1 and 0, I suppose, for completeness. Doesn't affect the answer, but it's there. Those are the digits that we'll get, and we'll see each of them 300 times. Okay. So can I do this sum? I think I can do this sum. This is like triangle numbers, right? Do I know enough triangle numbers to just know this? Could do the thing. 9 times 10 over 2 is 45. So this is 45 times 300. 45 is half a right angle, so times 3 is 3 right angles, is 135, and write 2 zeros on the end is 1, 3, 500, which is quite a lot. So what happens if you add up all the digits in all the numbers between 0 and 999? What a cool fact. Rilo's here. Hi, Rilo. He just joined in as we finished a math question. Nice to have you with us, though. And I think someone else earlier said that it was their first time watching live, so thanks for coming along as well. Okay. What an unusual question. Why an x, y needs a low space through this equation? I don't know what that means at all. Something about prime numbers and some squares and the number 71. Okay. Okay, right, let's have a look at some admissions-y chat stuff. Could do the poll again. Oh, I could do the poll again. I love a good what's next poll. I know I'm going to reset the poll, turn the poll on again, and see what happens, right? Okay, and I'm going to have a quick look at some stuff. So people have been asking this. Similar practice question. Oh, someone did the question like this in their school yesterday. Great to hear. I love that people are on that sort of thing. And they did the sum up to 99. So here's a good question. You can't see it on the stream because it's behind the poll. They did the sum up to 99 instead of 999. What else do you get for that? And we're going to go there. In general, if instead of summing up to 99, 1 less than 10 to the 2, or summing up to 999, 10 to the 3, what if I sum up to 99999, 10 to the power of k? Maybe I could use n. Have I got an n so far? No. Okay. What if I replace that with n nines as that number up there? How does this depend on? There's a there's a 3 in here, and there's kind of 100 effect going on, but it's kind of quite 3. How does this question depend on the fact there are 3 nines here, not 2 or 5? Cool, right. I don't think I phrased that question well at all. People want the just chatting now, I think. Or maybe a short question. Let's have the just chatting. Cool, I'll put the short question on the screen. This question is quite tough. If you want to talk about this question in chat, then I will occasionally read out your comments about this question. I think it's pretty hard. Cool, right. Sum to any number is super difficult. So if your sum is not going up to 999, if your sum stops early at like 536 or something, then it's pretty tough just to think about what that sum should be when you add up all the digits. And it's tough to think about. Writing down the final answer is not fun either. Okay, let's have a quick look at some questions that I've starred along the way. People are doing the n question. Okay. Adam, I'm gonna read that. I'm gonna read the thing about square roots and cosines. I've done the favourite college. I'm not allowed to say. Do I work with all the colleges evenly? Look, this is the sort of question. You might think I'm ignoring your question, but no, it's been starched to come back to you later, so I can dig it up from the depths. I work with all the colleges. Some of the colleges organise a lot more things that I can join in with. So if you're visiting a college and there's a maths thing going on, then that might involve me. So there's some colleges that I've worked with more, and they're all great. Okay, that one, AAB, gap years. We want to do gap years again? Could do gap years. So when you take a gap year, are they at a disadvantage? So not really, because usually when they're doing a gap year, they've finished their school leaving qualifications. So usually they've seen lots of extra maths and had more time to think about mathematics, which is, in some sense, quite an advantage if you're applying after qualifications. On the other hand, you've now got a year where you're not in school and you haven't started university yet, so on your gap year it's important to have something planned to keep your skills sharp, to make sure that when you start university you're ready to get going again, ready to do some mathematics. So I think knowing extra mathematics is nice if you're applying after qualifications, but having a plan to keep all that mathematics in your head is a good idea. If you apply before you're planning to do your gap year, then tutors at Oxford might like to see what your plans are to decide whether that's a good idea or not. If you don't have a great plan for your gap year, then it's possible that you get offered a place to start straight away without the gap year. So there's a slight difference there between applying during your gap year or applying before a gap year. Okay, right, good. Let's undo that and undo that. And people are putting in the question here. The spam's back. Great. I don't know why you'd spam this. All the places you could spam on the internet. I just say I don't understand. Okay. What have I got? Is A star B the same as A star AA? No, those are different. And importantly, Oxford doesn't use UCAS points, so up one, down the other is not equivalent. In terms of policy of how do we feel about A star B, well, that's different and it varies from course to course. But in general, no, A star B is not the same thing as A star AA, mostly because we're not using UCAS points. Okay, yeah, there was a question ages ago, Raf, you've reminded me of. Any advice for 6 and 7? Question 6 and question 7. So next week we're doing some mathematics on the computer science questions. We're looking at 5, 6 and 7 next week, with the usual sort of warm up and doing some other bits of mathematics and trying other stuff out as well. But we're going to have a little bit more of a computer science theme next week with an episode called Recursion, which is going to be a little bit different. Any advice for it? The questions often use less mathematics from the syllabus than the rest of the questions we've been talking about so far. So if you're applying for computer science, then it's sort of less important that you know about differentiation and polynomials. I mean, you've got to know the basics, but it's more important that you know how to adapt things like the kind of very primal stuff that we know about, sort of logic and truth and working things out. This question 5 that we did before, over here, nobody got to talk about this question. This question 5 that we did over here was written by the computer science department, I think, and it's one that computer scientists would do because everyone does question 5. You see it's got this kind of really logical structure to it, and it involves a nice idea. There's some counting. Not that computer science is all about counting, but having this kind of system of how we're going to do the counting is sort of important. Okay. Do universities? This is a good question. I like this. Do universities take the mark percentages of our A-level grades into account? For example, if one student got A star, 80% of the student got A star. No. Well, okay. So let's say for Oxford, we don't mind. We don't get that data. We don't. An A star is an A star as far as Oxford is concerned, which is a nice and simple policy. Other universities, you just talk to other universities about how they feel about this. There used to be such a thing as module scores that some universities looked at. Oxford doesn't do this. Good question. How picky are CS with grades? That's a question for the CS department, I think. If you email the undergraduate admissions people at computer science, they'll let you know. I think the person predicted A star B, so maybe check with them whether that's a big problem or not. I'm going to say ask the computer science department. Okay. Is YouTube crashing for anyone else? Good question. Always nice to check if I've got any viewers. Who knows? Explaining or under-explaining. Yeah, so question 6 and 7 often have a bit of explaining what you're doing or talking about your mathematics, which really is there. It's really there to make sure that people understand what they're doing, rather than just writing yes or no and guessing and moving on. If you see it more as, prove that you're not guessing, then that's quite an exam way to approach the sort of question. But if you see it as prove you're not guessing, then maybe you could be happier with the amount that you're writing. I suppose that, prove you're not guessing or jumping optimistically from... Is this a thing that, obviously not a thing that you do, but a thing that unscrupulous candidates might do, is to write down one thing that is true and then write down a thing that's very similar to the thing they're trying to prove with a big logical gap in between, jumping over the big logical gap from one side to the other without really explaining what's going on. Because it's really hard to know, you're a student, it's really hard to know when you're writing what the unscrupulous students are going to try and jump over. It's really hard to know, is this a big logical step or not? But in general, if it feels like you've had an idea or you had to do some work to get from one step to the next step, you have to think about it, then report back. Let us know that you thought about this, or you had give us something to show that you thought about it to get from one statement to the next. Maybe it was obvious to you, but maybe you have to think a little bit. Cool. Okay. Worried about Worcester College again. Sorry, I saw the question. I started it. Haven't answered it. I think it's the same person. Maths or maths and computer science, not 100% right. Yeah, it's really tricky deciding between courses, isn't it? So choosing between courses is just really tough. I think it comes down to, you could look at the overlap material. That's the stuff that you're really interested in, I suppose, the kind of algorithms and proof and knowing things for sure and writing efficient algorithms to calculate things. But you could also look at the not overlap. You could look at the bits of maths that you would not be studying if you did maths and computer science. You could look at the bits of computer science that you would not be doing if you did maths and computer science. That to make one course out of two that involves cutting out half of each course. So you could look at the bits that you'd be missing out on and see if you could decide based on what's not there rather than what is there. So this is like doing the difference operation, doing XOR on the two sets. Right, cool. What happens if I'm predicted A star, A star? Hang on, it's the same question 5 times. Okay, right, cool. I think we've answered this one. You can contact the CS department with their email address, I think is best, which is something like undergraduate.admissions@cs.ox.ac.uk. Cool. Worcester College, right, okay. Saw this question twice, sorry. Usually very oversubscribed. I think that's true. Worcester College is quite a nice looking college. Probably say it's not an admissions advantage. Do you think I have a lower chance of getting shortlisted in an offer if I apply to Worcester? You've guessed what I'm going to say. No, we're watching this really carefully, of course, because we also know that Worcester College, very pretty college, gets lots of applicants. We're watching it really carefully because we want to make sure that if you're a strong applicant who's applied to Worcester, then that's not a disadvantage. It's joking aside, I do a lot of this like funny stuff on live streams and we do MAT questions together, but the big part of my job, the reason I kind of get paid to work here, the big part of my job is to make sure that this thing works out. That people who apply to colleges with lots of other strong applicants aren't disadvantaged. So when I'm not messing around on live stream stuff, that's my actual job. Cool, right. Oh, here's another bit that's my actual job. How does the system of being assigned a second college work? We have a random algorithm for it. Are you considered for both? Is there pooling? It's random. We assign you a second college at random. If you're shortlisted, you get given a second college. It is random. Cool. If you reapplied, you have to retake the MAT. The answer to that one is unfortunately yes, because I'd like to make sure that everyone's taking the same MAT paper. I'm not going to take a gap year because of fee status. Okay. Again, so gap years again. Make sure you've got a plan to keep your math skills sharp in between. And I'm sorry that it's come down to the kind of fees and financing situation. This sounds quite unfortunate, really. Do extra bits of mathematics if you can. Find stuff on the internet. Find stuff to keep doing. Keep practicing bits and pieces. Revise your stuff, and should be all right. Cool. Is the answer to this question C? I can't remember. I'm not sure it is. Is C false? Oh, C is worded quite strangely, isn't it? People are going to talk about it in chat now because you've mentioned it. I'm not sure. I think C. So if pi n is 1, so this is a capital pi, by the way. If capital pi of n is 1, that means the number of distinct prime factors of n is 1. So it's a power of a prime. It's only got one prime factor. There are values of xn which are impossible. No, I think that's true. I think 0 is impossible. I think it's impossible for the last digit to be 0 if you're a power of a prime, because all the numbers that end in 0 are multiples of 10, and they've all got factors of 2 and 5. So their number of prime factors is at least 2. Oh my word, okay. Not C. Sorry. And they've said they're really wrong. Okay. Is it impossible to be 6 as well? No, I think 6 is possible because 2 to the 4 is 16. Pi of 16 is 1. It's got one prime factor. And x of 16 is 6. So 6 is possible. 0 is impossible. Yeah, that was true. Only one value. Okay. This is like the values thing, right? Because it says values plural. Yeah, I don't love it. I see why you've asked that. Don't love it. Yeah, really good point. Don't love it. Don't love it. Yeah, I'd like at least one value. Groovy. Okay. Good. Okay. What else did I miss earlier? Let's have a look. I've got 3 more things. I've got Adam's question about cosines. Gap years. Oh, can you visit Oxford, the university, at the moment? Sorry if you asked this like 20 minutes ago. Actually 15 minutes ago. Sorry. Some of the colleges are open to visitors. The maths department is not open to visitors at the moment. Sorry. There's not a huge amount to see anyway. Just lecture rooms. So probably not worth a visit to Oxford just to see lecture rooms. The town of Oxford is mostly open if you want to wander around and go to shops. Some of the colleges are doing tours outside mostly, I think. At the moment, some stuff is open. Oxford's spread across the city of Oxford. It's quite exciting. The colleges and the departments are in different places in the town. So, it's not like a campus university where everything's there and you could do a little tour around. It's like in the city. So it's a nice city. If you're in the UK, it's not that hard to get to from London, and it's a nice place. Okay. Almost at the point where I'm going to do Adam's cosine question. No, lots more questions. That's good. Do I prefer? Oh, right. Okay, it's gap years again. Are we ready for some gap year questions? The dude asks, do you prefer people not to apply for a deferral? So this is applying for gap year where I'm about to do the gap year and I'm going to start university a year afterwards. Do you decrease your chance of being offered a place by doing so? So, applying for deferral is tricky because you're asking to be reserved a place in a cohort where most of the people applying for that cohort we haven't seen yet. Most of them we haven't seen yet because most of them are going to apply next year while you're on the gap year. If we don't make you an offer, then you can apply next year during the gap year with the same plan of starting in the following year. And that means that we want people who, when we make people an offer for deferred entry, we want to make sure that they're people who are really good compared to the cohort we haven't seen yet. And I'm not going to say that decreases your chance because you've also got the option of applying the next year and then doing a thing without that effect. But there is an effect that if we're offering you a place for a cohort where we haven't seen most of the applicants for that cohort, we want to make sure that you're can be a good student on that cohort. Right, okay. Getting a little bit tired. Going to do the cosine question just to mix things around. And I've starred some more stuff. Entry requirements again. If you apply for joint honours and get an offer from only one department, this is possible. It's very rare. Most people have applied for the course that they want to study. It's not impossible. We do it in the maths and computer science world. I'd say maybe one person a year gets an offer for not the course they applied for. One a year maybe, average. One on average in maths and computer science, which are the courses I interact with the most. References are important. Asking the same question lots of times does not make it... Right, okay, good. Yeah, okay, right, let's do this question, because I recognise you've asked a lot of questions on a theme. I'm going to do this one, I'm going to do my cosine question, and then we're going to call it a day. Okay. I respect you've asked questions like this. I can see why it's important to you. Here's what happens. If you go beyond the entry requirements in your actual exams at the end of year 13 or equivalent, so in July 2022, but your predictions didn't quite meet them, then actually in the timeline, what actually happened was you applied and we've got your predicted grades. If we haven't seen your exam results yet because they're in the future, we've got your predicted grades to go on. We'd need a reason to believe that you're going to do well in those exams that are coming up in the future when we're considering your application. We make all our offers in January 2022 for this cycle. So our offers go out in January 2022. At that point, we've got to go on what we know from your application. So we've met you for interviews, we've seen your MAT score, we've got your predicted grades and reference and things like that. So reference is important because it's part of telling us that you're going to do well in school and meet the sort of meet the grades that we're looking for, or even say that you're going to exceed those grades and get better grades. Fine. Okay. At that point, we've got to decide in January, so months before you do your final exams, we've got to decide in January, do we want to make an offer or not? If we make an offer, then you need to get the grades. You need to meet the standard grades that we're looking for, or whatever it says in the offer. You've got to get the grades in your offer text. That's actually a legal requirement to be able to start the course. If we don't make you an offer, then unfortunately it doesn't matter what grades you get in the exams later on. If we don't make you an offer, then I'm afraid you don't get to start the course, even if you go and outperform in the exams later on. So it really comes down to when we make the offers in January 2022, based on things that we've seen like the maths and interviews, if we shortlisted you and other information that we've got, do we think that this person is going to be able to get the grades that we look for, which is A star AA for maths and computer science, A star AA for computer science, A star A for maths. Do we think this person's going to get them? Normally, predicted grades say, yep, sure, it's going to be fine. If your predicted grades aren't up to that standard, then we're going to need some reason to think that you're going to do better. Yeah, okay, right, good. Okay. I said I did the cosine one. I think I can see other better questions coming in. Wonder if I should do them instead. Yeah, people are asking fun questions. Okay, sorry, Adam, and your cosine question, I will type an answer later. The cosine question was miles back. Adam asked a really good question about a past paper question about cosines. Asked it in the middle of doing something else, so I didn't do it live. Cool. Right, okay. This week, so on screen at the moment, we've got one of my referees says nothing about the grades I didn't get yet. Your referee will be asked to predict grades. It's part of the UCAS interface. They will be asked to predict grades in the qualifications you've got coming up. Do I think Riemann hypothesis or twin prime conjecture will be resolved within the next decade? I'm going to be pessimistic and say no. Sorry, I think they're both too hard. Rebecca says this week modular arithmetic would help, but is not listed on the syllabus. Do you have a list of topics which are useful to know, but not strictly on the MAT syllabus? I don't have a list. I think there are probably quite a few things that would be helpful. In some sense, the more maths you know. Yeah, it's tricky because the more maths you know, even unrelated mathematics, some of it's helpful in the sense that you've just seen and experienced more stuff. So when you see a maths question like this, maybe you've already seen a big capital pi somewhere else, so it's less scary to you because you've already seen a big capital Greek pi. But I don't feel comfortable making a list of go and look at the Greek alphabet because that's not actually a useful skill in the rest of your life. And is my list just going to be learn loads of extra maths? You're not supposed to need modular arithmetic to do the maths. I'm not a huge fan of questions where if you've seen extra bits of mathematics, they get really easy. Some of these questions are a little bit easier, especially in the warm-up, which is not math questions. They're a little bit easier if you've seen things like modular arithmetic. But some of that's unavoidable because we want to ask questions using multiples of things. And some people know loads of facts about multiples of things. Unhappy truth. Unhappy truth or happy truth? Taking 4 gap years, mainly for financial reasons. Is that too much of a disadvantage? So 4 gap years, you need to keep your skills strong. I think you now count as a mature student. There's advice on mature students on our website. I will link it to you in the comments once I'm not live. I'm not in regular school. Finished early. How much should I talk about that? You will know from your education history on your UCAS form. You can talk about it if you want to, if you think it's relevant. If you're doing lots of independent study, then you could spin that and tell us that you're already doing lots of independent study, just like university. So you could mention that in a positive way. Let's wrap it up here. Someone has put the bold claim in chat. Admit me to Oxford, and I will solve both conjectures, not just one. They will solve both conjectures. Right, okay, thank you, chat. I'm going to wrap up partly because... Oh, Adam's still here. Oh, I'm really sorry, Adam. I never got back to your cosine question. I'm so sorry. I'm going to go and read your cosine question and type an answer. And other people whose questions I haven't quite answered, I've been starring them. You can't see the stars, but I've been starring them on the way through. I'm going to wrap up the live stream there, I think. I'm losing my voice. Right, cool. Sorry, everyone. We'll see you next week for some recursion. Bye.